Let's begin by considering the effects of a variation in inlet pressure. For our discussion, consider that the following compressor draws atmospheric air through an inlet filter, as seen here. The rated compressor inlet pressure is 14.5 psi. The discharge pressure in this example is 20.6 psi. When the filter becomes dirty, the inlet pressure at the compressor flange drops to 14.2 psi. What is the effect on discharge pressure and shaft horsepower at the rated inlet volume flow? Now for a centrifugal compressor, the discharge pressure is related to the adiabatic head, according to the following equation. Here, Z sub 1 is the gas inlet compressibility. Capital R is the gas constant. T sub 1 is the gas inlet temperature. K is the ratio of specific heats of the gas. And small r sub p is the gas pressure ratio. Please note that subscript 1 refers to the compressor inlet or compressor suction. Subscript 2 refers to the compressor outlet or compressor discharge. Now, recall that for a given inlet volume flow, at a given rotational speed, the head output is constant. In our case, because there is no change in the other inlet conditions, then the pressure ratio does not vary. Therefore, the pressure ratio for the clean condition equals the pressure ratio for the dirty condition. The pressure ratio for the clean condition is equal to 20.6, which is the discharge pressure, divided by 14.5, the inlet pressure when the air filter is clean. This yields 1.42 as a pressure ratio for the clean condition. On the other hand, the pressure ratio for the dirty condition is equal to P sub 2, the unknown discharge pressure, divided by 14.2, the inlet pressure when the air filter is dirty. As seen here, P sub 2 equals 1.42 times 14.2. This gives 20.2 psi as a new discharge pressure for the dirty filter. So as seen here, for a centrifugal compressor, a decrease in the inlet pressure will result in a decrease in the discharge pressure. Now, to assess the effects of a variation in inlet pressure on power requirement, let's first refer back to the volume flow equation. Rearranging it gives the following equation. Comparing this equation with the shaft horsepower equation, which was discussed in a previous video, we find that shaft horsepower is proportional to weight flow or inlet pressure, as seen here. Please note that this last equation is not strictly valid because shaft horsepower is composed of gas horsepower and mechanical losses, as highlighted here. The mechanical losses are approximately constant for a given speed, but are in general a small part of the total horsepower. Therefore, ignoring mechanical losses will usually yield a useful approximation in our procedures. Now, starting from this general horsepower equation, we can write the equations corresponding to the clean and dirty conditions, as seen here. Dividing SHP sub dirty by SHP sub clean will yield the following useful relationship. As you can see here, the shaft horsepower is proportional to the inlet pressure. After substituting for P sub dirty and P sub clean, it becomes obvious that a decrease in inlet pressure will result in a decrease in power requirement. In this example, we have voluntarily ignored the effects of system resistance downstream the compressor. For many applications, system resistance is small when compared to the total pressure requirements of the compressor and will therefore have minimal effect on the analysis. In some applications, however, system resistance effects are large and will actually define the compressor operating point. We can view system resistance as the sum of piping, system losses, and utility pressure drops. These should not be thought of as losses. As the volume flow through the system increases, frictional losses increase and will require a higher pressure at the discharge of the compressor to be overcome. The following figure shows a typical system resistance line superimposed on two compressor performance curves. The solid curve represents the rated inlet conditions. This curve is provided by the manufacturer of the compressor. The dashed curve shows the effects of a reduction in inlet pressure only. The intersection of the system resistance curve and the rated inlet condition curve is the rated operating point. In this example, we have assumed constant inlet volume flow and therefore calculated the discharge pressure at point C. The power requirement calculated previously using the following formula was also for operation at point C. If the compressor in our example operated with system resistance, it would search its new performance curve, so the dashed line, until it intersects system requirement. The result would be operation at point B, as highlighted here. Therefore, the inlet volume flow would be somewhat less than rated, and the discharge pressure would be slightly higher than calculated. At this stage, don't worry if some of the concepts highlighted here are not clear enough for you. We will break them down into easily digestible concepts further ahead.